And we're going to do 3 of these proofs together. And so the idea is we are now going to be applying all those properties and everything that we've been talking about into geometric proofs. All right, so let's start with, we're going to do A first, proof A. And proof A says you're given that ray TV is a bisector of this angle. And then you're trying to prove that over here, ray TY is also a bisector of its angle. So obviously the given is going to go in our first step there. So ray TV bisects angle UTW. That's given. Okay, how do you go from step 1 to step 2?
It's the definition of an angle bisector.
Is the definition of an angle bisector. Because it's an angle bisector, that means the 2 angles are congruent. So it's the meaning of the word bisector or angle bisector. Okay, so we've used step 1 now to get to step 2. The difference between the proofs that you do that are just solving algebraic equations and the ones where you're actually doing a geometry proof are that they're in geometry proofs, it's a lot more common to have multiple steps that you have to kind of go back up further in the proof to find to combine with a current step. Or you maybe have to go to the diagram and find something and bring that into the proof. Or maybe there's more than one given and you're going to go and use the first given in the first spot and then go grab other givens. With the algebraic equation ones, typically you're going, here's the step, now do this, now do this. You're just kind of going like step by step. There's not as much like substituting and things happening. All right, so angle 1 is congruent to angle 3 and angle 2 is congruent to angle 4 is not coming from step 2. It's coming from the diagram. Okay, where is angle 1 congruent to angle 3 and angle 2 congruent to angle 4 coming from? It's not coming from step 2. Oliver, do you know where that's coming from?
It's deduced that it's definition of vertical angles.
Okay, it is. That's a really common mistake. It is because they're vertical, but it's not definition. The definition of vertical angles would be if you just looked at the picture and said 1 and 3 are vertical angles or 2 and 4 are vertical angles. So if it just identified, okay, if I wrote in the proof, and sometimes this might show in a proof, but if I just said angle 1 and angle 3 are vertical, if I just identified them, like I know what vertical angles are, and those are vertical angles, then the reason would be definition of vertical angles. But that's not what this step is saying. We're kind of skipping that step and saying these are vertical, therefore they're congruent. So that's actually the vertical angles theorem, or you can just write vertical angles are congruent. But it is not the definition. And again, that's a really common mistake, but you want to make sure you kind of get that straight. Sometimes they might put a step like that in right here prior to stating that the angles are congruent. So if they just identify that the angles are vertical, that would be definition of vertical angles. And then saying that they're congruent is vertical angles theorem. They're congruent because they're vertical is not the same thing as a definition. Typically, we skip that definition step. And so typically what you will see in proofs as reasons will be vertical angles theorem and not the definition of vertical angles. Okay, so that's coming from the diagram. It's not actually coming from step 2. Step 3, however, is going to combine steps 2 and 3. Step 4, sorry. Step 4 is going to combine steps 2 and 3. So what's the reason for 4? Rachel, tell me what you think.
Is it the substitution property of congruence?
Okay, so Jack, tell me what you think about that.
I think it is subtraction property of congruence.
I think it's transitive property of congruence.
That's Nyla.
Yeah.
Thank you, Nyla. Tell them why it's not substitution.
Because there's no substitution property of congruence.
Good. When you're doing substitution, they have to be equations, okay? If it looks like substitution, but it's congruence, it has to be transitive. Substitution's only for equations. So is subtraction. I forget now who said that because it's been too long. But subtraction is also a property of equality. So when it's congruence, it can be transitive property of congruence, it can be reflexive property of congruence, it can be symmetric property of congruence, or it could be something like definition of congruence or like vertical angles are congruent. It could be something else that's not a property, but substitution will never work for congruence. It's only a property of equality. So if you did that on the quiz, your grade is going to show that a little bit. Okay, so those two together are being used, and this is how it's transitive. So if you started with angle 3, because I'm trying to go from the left side to the right side, okay? So if I started with angle 3 is congruent to angle 1, angle 1 is congruent to angle 2, angle 2 is congruent to angle 4, therefore angle 3 is congruent to angle 4. Okay, we're linking them together. And again, it's like those little trains that are magnetic that you put together when you're a little kid and you like match them up end to end. They only go together one way. Or the little monkeys that have the curly arms that you can link them together. You need to be able to start with the left side and end with the right side, and then it's transitive. But again, it will not be substitution. If you're having that problem remembering that, write it right here, not substitution because it's congruence. Okay, so we use 2 and 3 together to get 4. Now we know what we were proving, right? We were proving that ray TY bisects that angle. I'm just going to copy that and paste it down there instead of rewriting it. We know that that the last statement needs to be what we were proving. That's how we know that will be done. And it's coming from step 4. We're at the end and we haven't used step 4 yet, so that clearly needs to be used. So if angle 3, let's go to the picture. If angle 3 is congruent to angle 4, what makes this an angle bisector?
The definition of a bisector.
Definition of an angle bisector. Yes, that's what it is. So notice that in this proof, we went from ray TV is an angle bisector to saying that the angles were congruent. And at the end, we went from the angles are congruent to saying that that ray TY was an angle bisector. Remember that definitions are biconditional, so they can go both ways. You can go from it's a bisector to the angles are congruent, or you can go from the angles are congruent to it being a bisector. So that is definition of angle bisector, because you're like, I don't know what an angle bisector is, and that's what it is because the two angles are the same. Okay, so as you're going through these proofs, again, it should be that all the steps that are stated someplace up above get used before you get to the end. And if there's anything you haven't used, then you're probably missing something, because proofs should not have stuff over here in the statements that isn't actually used anywhere else in the proof. So if you kind of keep track of what you've used as you go, then you can kind of watch out for things that you haven't used yet. And that can sometimes be a clue for, you know, maybe where it's applicable down below when you get stuck. All right, and again, the pieces of a proof, remember, are the given and the prove. That's your if, then. That's your hypothesis conclusion. Then you'll have statements, then you'll have reasons, and then you typically have a diagram when it's a geometry proof. All right, we're going to jump down to C, which is the top of the second page on the left side. This one's going to be with segments. Okay, so it says that segment AB is congruent to segment XY, and segment BC is congruent to segment YZ. And then you're proving that the whole segment here is congruent to the whole segment there. Hopefully that's believable, because you're adding, you know, the two of the same lengths together, and of course the whole thing should be the same. So the argument here is explaining step by step why that's true. Okay, so our given is going to be segment AB is congruent to segment XY. I'm going to do a quick little glance here and see if there's anywhere down below that I might need to use the other given. Sometimes with the geometry ones, you'll have more than one given, and it may be used all at the beginning. It might be sprinkled throughout the proof. So when you start, you want to kind of look and see, is there anywhere else down below that there was a part of the given? Well, all of those are equations, so that means that the congruences must have been at the beginning. Segment BC is congruent to segment YC. Okay, that's given. Okay, Ainsley, what is it when you go from the segments are congruent to saying that their lengths are equal? What's the reason for step 2?
Definition of congruence.
Good. Now, I was seeing some students, you can either say congruence or congruent segments. I was seeing some students write things like definition of equality. That's not a thing. Definition of equality is not something you'll ever write on a reason of proof. The other thing I was seeing sometimes is definition of segment. That's not the definition of a segment. You're not saying, oh, there's a piece of a line that is consisting of 2 endpoints and all the points between them. It doesn't say like segment AB is a segment. Okay, it's definition of congruence because you're saying, I know what congruent means. Congruent means that they have the same length. So we've used step 1 to get step 2. Okay, step 3, AC equals AB plus BC. XZ equals XY plus YZ. That is not coming from step 2, it's coming from the diagram. What is the reason for that? Evie, can you tell me the reason for AC is equal to AB plus BC? And XY plus YZ is XZ?
Would it be addition property of equality?
If it's addition, like let's say you had gone from this step up here and you had added the left side and added the right side, then addition would have said AB plus BC equals XY plus YZ. And that's not what it says. It says that this is equal to a sum and then this thing is equal to a sum. It's actually coming from the diagram. Look at the picture. Tell me why, what is it when you look at the picture and say this plus this is the whole thing? What is that?
Angle addition postulate.
But they're not angles there.
Oh, segment addition postulate.
Right. So on this one, again, we're kind of pausing on step 2 and saying, okay, hold on a minute. Let's jump away from step 2, look up at the picture, and we can say that on the diagram, the 2 pieces add up to the whole. Okay, that means we haven't used step 2 yet. So kind of keep that in mind. We're going to have to be doing some combining and some stuff with steps 2, 3, and 4 here as we go along. So for step 4, remember we have everything from 2 and everything from 3 we haven't used yet. Where do you see, so XZ equals AB plus YZ, where above do you see something that's really similar? Where is there an equation that looks a lot like the step 4?
Step 3.
Step 3. So this part of step 3 looks a lot like it, right? The difference is that instead of XY, we have AB. Why are we allowed to do that? Why are we allowed to take out XY and put AB in its place?
Because in step 2 it says AB equals XY.
Because in step 2 it says AB equals XY. So using this, we can say, okay, let's go ahead and put that in down here. And so what is the reason for that? Luke, is that substitution or transitive or something else?
Substitution.
Is it also transitive?
Yes.
It is not transitive because you're only replacing one part of the equation. If it was transitive, you'd have to be, because like you'd be using this equation and this equation, and you'd have to have a whole side that crosses out. Well, here's thing 1, here's thing 2, here's thing 3, here's thing 4. There's not a whole side that matches in the equation in 3 and the equation of 2. So it's not transitive, it's only substitution. You just took out this one term and you put in something new. Okay, so that one has to be substitution, not transitive. Okay, so we've used part of step 3 and part of step 2, but notice we still have a few more things we can use up there. Okay, from 4 to 5. What is the difference with the equation 4 and the equation 5, and why would that change allowed? Why are we allowed to turn step 4 into step 5?
Because BC equals YZ.
Okay, BC equals YZ, right? So we can just say, all right, let's take YZ out and put BC in its place. And we know that that's allowed because they're equal up in step 2. Lily, is that substitution transitive or both?
Just substitution.
Just substitution. Because again, you're only replacing one term. Do that. Okay, number 6. So it looks like we've used all of step 2 now, but there's still part of step 3 we have not. Number 6, AC equals XZ. The equation in 3 and the equation in 5.
Is it transitive property?
Okay, tell me why.
Because you're taking the whole side of the equation from number 3 and the whole side of the equation from number 4, putting them together.
Number 5, right?
So yeah, that's what I meant.
Both of them have AB plus BC. We can cancel those out. We can replace that. We can take it out and go from straight from AC to XZ. Again, transitive is like an intermediary. Transitive is like if you owe one of your friends $10, so you give it to a different friend and say, hey, different friend, give this to my, this other friend. And then instead of that, you could just give it straight to the friend who you actually owed it to. Okay, so that one you could call transitive. Could that be substitution also or no? I agree with transitive.
Yeah, it could also be substitution.
It could also be substitution. So that one, it's transitive because you're taking a whole entire side of the equation out. It's also substitution because you could, let me point this in a second here. You could say, all right, I'm going to take out, let's see, in place of, I'm going to plug this XZ into AB plus BC. So I'm going to leave AC where it is, but I'm going to take AB plus BC out, and I'm going to put XZ in its place. And then I'll have AC equals XZ. So you can consider it substitution, or you can consider it transitive. Okay, this one actually is transitive because the whole side can be wiped out as compared to the last two, which could only be transitive. That one could be either. Good. Okay, and then number 7, we're at the end, so we know it has to be the proof statement. Segment AZ is congruent to segment segment AC is congruent to segment XZ. And Eli, what is that?
Definition of congruency.
Yes, good. That one is definition of congruence. So you can say definition of congruence, definition of congruency, definition of congruent segments. Okay, but that one is going from equality to congruence. So again, oh, and by the way, we used 3, 4, and 5 all kind of like mixed together there to get step 6. 6 is leading us to 7 because we're saying, for color I haven't used, purple. Okay, in step 1, we said that the segments are congruent, therefore their lengths are equal. And then in step 6 to 7, we're saying the lengths are equal, therefore they're congruent segments. Again, definitions are biconditional, so you can either go from equality to congruence or from congruence to equality. So you'll see at the beginning and at the end on this one. The reason that they had to go from congruence into equations is because you can only do things that are like addition, for example, with equations. So whenever they're going to bring in the segment addition postulate, they have to go from congruence into equations so that they can do segment addition and substituting and all that stuff. Okay, so for the first one here, we've got, remember that means perpendicular. That's our given. Perpendicular means that they make right angles, right? So if OA is perpendicular to, where's OA? OA is perpendicular to CD. So if those two are perpendicular, they make a right angle. And if these two are perpendicular, they make a right angle. So that is the definition of perpendicular. You can say perpendicular, or you can say perpendicular lines. You can also say perpendicular lines form right angles. Okay, from 2 to 3. Because they're right angles, that means their measures are 90. That is the definition of right angles. That's what it means to be a right angle. Okay, for number 4, you can either say they're both equal to 90, so they're equal to each other, or you can say you're substituting in place of the measure of angle XOB. Sorry, in place of 90, you're putting in the measure of angle XOB. So that's either substitution or transitive. Again, you don't have to write both. One or the other is fine. But those are properties of equality. And that could be either substitution or transitive. Number 5, so basically 1 led to 2, 2 led to 3, 3 led to 4. 4 is not leading to 5. 5 is coming from the picture. So you're saying that when you add up that angle and that angle, you get the big angle. And same thing with 2 and 3. So that is angle addition postulate coming from the diagram. Okay, and then for number 6, we're sort of using 4 and 5 together. So we're saying, okay, you could take measure of 1 plus measure of 2 and put it in place of measure of angle COA. And you could take 2 and 3 and put it in place of XOB, and then you'd have this equation. Or you could also call that one transitive. So you could say measure of 1 plus measure of 2 equals the measure of COA. Measure of COA equals measure of angle XOB. Measure of angle XOB is equal to the measure of angle 2 plus 3. So therefore, 1 plus 2 equals 2 plus 3. So that one is also transitive or substitution. And then in the last one, to get rid of that measure of angle 2, you're saying how to take that equation and turn it into the measure of 1 plus is equal to the measure of angle 3, which is what we're trying to prove. To make that disappear, we're subtracting the measure of angle 2 on both sides. Okay, that cannot be transitive because we're not combining two equations together to remove a side of an equation. We're just subtracting away that one term. Okay, so 6 led us to 7 and substitution.